The third presentation is from King Abdullah University of Science and Technology, and the title is Numerical Simulation of the Chemiluminescent Species in Lifted Triglacial and Obtained Laminar Phase in flow. And the work is presented by Dr. Numerical.
So this is work done by me, my immediate supervisor, Fabrizio Bisetti, and NC13 developed a clinical model. Everybody knows Combustion, and SIAM is the PhD student who made photographs that will be presented later. So first, those who don't know, if somebody doesn't know, when flame propagates through fuel/air mixing layers, it may exhibit trilateral structure, especially if the fuel is stratified, ranging from lean to rich. The trilateral structure is also called triple structure because the flame is composed of three flames, the lean premixed and the rich premixed wings, together with the diffusion flame, all extending from a single point. So denoted as the trilateral point in this figure. The fact that all three flames they coexist in a single point suggests that this edge of the flame will be located along the stoichiometric line. So the motivation for this work is that we are simulating this trilateral structure using the complex high hydrocarbon fuels. So we have to count on the fuel decomposition and differential diffusion. The laboratory was all about fuel and heptane decomposition. We are going to investigate the stabilization characteristics, the lift of high reattachment, and we will use the chemiluminescent species in this mechanism to analyze the flame. However, this is just like results work in progress because we are going to do this for the low temperature regimes, and at this point we have analyzed this for the high temperature regime as this is like a stepstone. The goal of this presentation is to present a parametric study for you and show you the structure and the behavior of the trilateral flame with the complex hydrocarbon fuels, and then find the correlation between the chemiluminescence and the leading result and other parameters, and compare the actual chemiluminescence with the actual photographs of the flame. For the numerics, we use the low Mach number reactive flow in an axisymmetric domain with second order finite difference keys, and we use the pressure correction step involved in the solution of the Poisson equation. We solve the system in the multi-grid precondition conjugate gradient iterative solver on massively parallel machines. The solver transfer is negative. All of this is performed using the MGA from the developed at the Stanford University, which is a finite difference method, especially on spatially and temporally staggered grids with a semi-implicit fractional step method. For the model, the chemical model, we use 97 species model and 700 reactions developed by Professor Sarati. It started as the detailed model from the Livermore for the N-heptane. The mechanism was reduced using the DRG approach to 150 species and then further reduced by manually removing the species to 97, with special focus on the chemiluminescent species that gave the pathways the pathways the previous presenter. So to validate this 97 species mechanism, we do two tests. First, flame speed propagation, which we are focused on here. And as you can see, the present mechanism, the blue squares against the red circles, especially in the near stoichiometric mixtures where the experimental uncertainties are smaller. You can see very good agreement, and it falls within the experimental uncertainties in the off-stoichiometric mixtures as well. For the second test, we use the opposed flame configuration, where you have fuel on one end and oxidizer on the other hand. The fuel's temperature is fixed to 378 kelvins, and the temperature of the oxidizers is being gradually increased until the ignition occurs. So here you have the oxidizer temperature at ignition against the strain rate, and you can again see that all of the results of the present 97 species mechanism, the blue squares, falls within the experimental uncertainties of the experiments from published by SIAM. It's even better than the numerical results from the same publication. So this is the experimental setup. It reflects the computational setup. Reflects the experimental setup. We have a burner and with the N-heptane/air in the input surrounded by the heated top flow, and the bulk velocity, the inlet velocity ranges from 1.4 to 1.6. The top flow velocity is fixed to 1.4 in all cases. The inlet temperature ranges from 5 to 700 Kelvin. The fuel mole fraction from 3 to 4%. The resulting Reynolds numbers are below 100. So we are using two meshes. One is closed, one is refined. The closed mesh is used to reach the steady solution. It takes around 6 to 12,000 CPU hours. Depends on the case, and then if not satisfactory, if the solution is not smooth enough, steady but not smooth enough, we restart with a refined mesh with double number of grid points, which for additional 3,000 CPU hours. This is the parametric study. It's a height above the burner in all three cases against inlet temperature, the inlet velocity, and fuel mole fraction. The height above the burner is measured as the distance between the burner and the edge of the flame, as you can see in this figure. You can see the expected tendencies with increasing temperature, lift-off height decreases, as well as with increasing fuel mole fraction. With the increasing inlet velocity, the lift-off height increases. You can see that the comparison of the lift-off height with the experiments indicates less than 5% difference. The flame structure, as I said at the beginning, is rather complex. It has three flames: lean, premixed, and rich premixed rings, together with a trailing diffusion flame. Now, to identify these regions in the flame, we use the Takeno index that was developed almost 20 years ago. It's a dot product of two gradients: the gradient of the mass fractions of fuel and the gradient of the mass fraction of the oxidizer. So, if these two gradients are aligned, the resulting value of the dot product of these two gradients is going to be positive, marking the premixed picture, the premixed flame. If the flame goes from one side of the flame sheet and the oxidizer goes from the other side of the flame sheet, the dot product of these two gradients will be negative, denoting the non-premixed picture. So if you choose this fuel as an N-heptane, you can notice that we have no differential diffusion flame. Now, why is that? Because this Takeno index was developed a long time ago when the chemistry was, one-step chemistry was mostly used. We had only one fuel, one oxidizer, no differential diffusion. Now, once you have the interpretation of this Takeno index, is a little bit trickier. It depends on the choice of the fuels. For example, the reason why we don't have the diffusion flame here is because once this NC13, the N-heptane, crossed the premixed region, the excess hydrocarbon in this N-heptane got converted to CO. So if you choose the CO for the fluid, fuel, you can see that the diffusion flame is present there. Now to support this, you can see that if the CO, the mass fraction of the CO is present mostly between the rich premixed flame and the stoichiometric value. Now you can see that the diffusion flame goes along the stoichiometric value. For the chemical luminescence, as it was explained in the previous talk, is the light emitted by the molecules in the excited energy state. It's a non-intrusive diagnostic tool, and it can be used as a hidden rate marker or even an equivalence ratio sensor. These are the most common species. We are using only two for our purpose. These are the wavelength at which they emit. So here we have the results for the mass fractions of the chemiluminescent CH against the Hiddelis rate. You can see there is some shift in the maximum zone, but they have a similar shape. If I do this horizontal cut, You can see that the relative proportion between the rich premixed and the lean premixed stream, this is the rich premixed stream, lean premixed stream, here is the diffusion, is relatively satisfied in both cases. Now, to compare these results from the numerical simulations with the actual photograph, photograph of course doesn't look like this. I have to line of sight integrate the results around the axis of symmetry here. So how would this look like? This is like a XY cut. So how would it look like if I look at it from the front? So if I do this integral, the results are going to have this nice flame shape. Of course, the results are mirrored around the axis of symmetry to make the full image of the flame. So this slide confirms that even after the line of sight integration, these contours here are the heat release rate. This is the chemiluminescence CH. When the horizontal cut is here, you can see the relative proportion between the rich premixed and lean premixed streams is still satisfied. Here you have the CCD images of the CH star and OH star, the chemiluminescent CH and the chemiluminescent OH. These are the actual experiments. They all fall within 1 centimeter distance. You can see that for increasing temperature, the diffusion flame enlarges. However, the width of the flame remains unchanged, both for CH star and OH star. To compare these experiments with the computation, you can see that even the computations, when in a black and white scale, they show the relatively well correlated results. So it's safe to say the computations do a good job representing the experiments. Again, you can see with the increasing temperature, you have the same tendency that the diffusion flame increases. To make this qualitative comparison a little bit more quantitative, here I take these dashed lines in the same positions in both experiments and computations, and extract the chemiluminescent values from the computation and the gray score intensity from the experiments. Now here you can see the comparison, they almost overlap. So this confirms that the computations, they represent the reality. Here you have the comparison of the experiments and computations for the OH star. So here you have the experiments and the computations. You can again see that the lift of height, the width of the flames, they remains unchanged with the increasing temperature. However, the height of the flame enlarges with increasing temperature. And they correlate the OH computations with an OH experiments. So in the conclusion, you have CCD images of the flame. We confirm that the CCD images correlate well with our computational results. We've also confirmed that the CH star correlates well with the heat release rate, so it can be used as a heat release marker. Take the photograph and you can know where the heat release rate maximum is. The parametric study proves that this mechanism that we are using correlates very well with the experiments, surprisingly well. Currently, we are working on the reattachment and propagation speed. As I said before, we want to go to lower temperature regimes and explore the ignition regimes in the higher, different regimes at higher temperatures as outer ignition. Thank you.
So we have a lot of time for questions.
Regarding the slow development of the expected points,
Can you repeat the question? Speak louder, please.
At those low Reynolds numbers are expected there are some good number of effects, buoyancy effects, because essentially absolute instability in the system
Experimentally, we didn't observe an answer. We didn't observe it experimentally.
Did you have experiments or says 96 experiments? Did you do the repeat the experiments?
Yeah, we repeated the experiments.
Yeah, the experiments have been repeated over several months. The computation has varied. So this computation is stage.
What is the command?
Delay calculated.
Your question?
What about the comparison OH star and T-freeze? You have a similar picture in your shown us? So I'm referring to your computations.
Yes.
You had side by side the freeze rate and CH star.
Yeah, I don't have the picture to show you, but you can see here when you notice when I compare the CH star with OH star, the maximums will be in a similar position. But I don't have the picture to show. In extra slides, I have more comparisons of these computations against the experiments. This is the CH star for 600 Kelvin. This is CH star for 700 Kelvin. You can see that they still have. Here is the OH star versus the computation versus the experiments 600 and 700 Kelvin. In this case, it's a little bit worse. We have this the width of the flag. This one is the best one.